Good morning, ma'am. My name is Kalyan Chakravarti, ECE branch. Today my topic name is wave propagation in lossy dielectrics. Wave propagation in lossy dielectrics. Introduction to lossy dielectrics. Lossy dielectrics are materials that exhibit both dielectric properties and energy loss during their propagation of electromagnetic waves. These materials are characterized by complex primitivity which includes both real and imaginary components. Understanding wave propagation loss dielectrics crucial for application in telecommunications, radar and other fields involving electromagnetic waves. Basic concepts of dielectrics. Dielectrics are insulating materials that can be polarized by an electric field affecting wave propagation. The dielectric constant of permittivity quantity, how much electric field energy is stored in the material. Lossy dielectrics different from ideal dielectrics due to energy dissipation, which is represented by the imaginary part of permittivity. Complex permittivity. Complex permittivity of loose dielectrics can be expressed as sigma, where sigma is a real part of conductivity. Epsilon is a conductivity. Wave equation is loose dielectrics. The wave equation for magnetic waves in loose dielectrics incorporates the complex permittivity into account for attenuation. The general form of the equation can be derived from Maxwell equation and involves both electric and magnetic fields. Solution to the wave equation reveal how wave amplitude decreases exponentially with distance due to losses. Attenuation and phase constant. Attenuation and constant measure how quickly wave amplitude decreases in propagates through the material. The phase constant beta represents the change in phase of the wave as it travels through the loose dielectric. The relationship between this constant helps predict the behavior of waves in various applications from communication to sensing. Frequency dependence. Wave propagation characterization in loose dielectrics are highly frequency dependent, affecting attenuation and phase velocity. At higher frequencies, the loss typically increasing, leading to great signal degradation. This frequency dependence is crucial for designing circuits and communication systems that operate at significant frequency. Temperature effect. The properties of the loose dielectrics can be significantly affected. Temperature change alternating conductivity and permittivity. Higher temperature typically increasing the mobility of a charge carriers, resulting in greater loss. Understanding temperature effect is visual for materials used in environments with variable thermal conditions. Application of loose dielectronics. Loose dielectronics are used in various applications, including microwave devices, antenna, and RF components. They play a critical role of design of a capacitor, insulators, high frequency circuit. Additional loose dielectrics are institutional medical imaging technologies such as MRI, where wave propagation is involved. Measurement techniques accurate the measurements of a dielectric properties essential for understanding wave propagation in loose dielectric techniques such as a time domain spectroscopy and impedance spectroscopy are commonly used to characterize the material. These measurements helps in development optimization materials for specific applications. Future dielectrics research into loose dielectrics ongoing with focus in developing new materials with the tailored properties specific application in measuring technologies such as the material and nano components from us to ends performance in wave propagation. Understanding wave behavior loose dielectrics with continue to visual as a communication seasoning technological level to feel free to modify any of the content or structure to better suit your presentation needs. Thank you, ma'am.